All right, so now we're in part 3 of this section on coupled oscillations. We did quite a bit of work already, actually. We have a framework to calculate the frequencies of a system of n-coupled oscillators. So that's really nice. That's what we did in part 2. And in part 1, we looked at a specific example using Newton's law. Okay, so maybe that convinced you what we did in the second part, that Lagrange formalism is actually pretty useful. I hope it convinced you if you were not convinced yet. And this section 3 is going to be a pretty short one. This is the result here is very important, and frankly, the most important result is shown here on the yellow box. Remember, the A's are the solution of the problem, of the algebraic equation. So we already found a way how to find omega square. Here it gives you the A's. So the index j and k's actually go from 1 to n. They correspond to the coordinates, and the index r and s also go from 1 to n. They correspond to the different n omega square that we find from solving the secular determinant. This equation here that you have in the yellow box is the main result. It's basically an orthogonality, or in fact an orthonormality equation that says that the A's between themselves are either orthogonal if we use the solution of two different modes, so if R and S are different, and they are orthonormal, so it's equal to 1, the sum is equal to 1 when R is equal to S. That's a very important result that we are going to use again in a later section. And frankly, if you are short of time, you could actually skip this screencast, so long as you take note of this result. But if you have 5 minutes, well, stay with me, and I'm going to prove to you how you find this equation. So this equation that we found in the last chapter was this algebraic equation that we obtained from the equations of motion and by trying an oscillatory solution. Again, the A, Jk, the coefficients of the Hessian of the potential energy, and the Mjk are the coefficients that we need to calculate the kinetic energy. So we can actually rewrite this fairly simply like this. We can always write this, and we can also write this so this is written for the mode S, right? This is when the k in the equation, remember I told you k was actually indexing which system we are looking at. But here, if we rewrite things a little bit for the different equation, we obtain this equation. I need to tell you a little bit something. How do we go from one index for A to 2 indices for AKS on the second equation? Is because we have a different A for each equation, right? And we have k going from 1 to n. That's why we have this term. We can write the same equation for R, and we obtain this equation. The same equation is just another mode, all right? And one thing we did is to say that we are actually using the symmetry for M and A. That's what we are going to do. So we are going to use a usual trick. We are going to multiply the left and the right-hand side of those equations by the top equation by AJR, so the left and right, and the bottom equation by AKS, and we are going to sum over J. All right, so we certainly certain that these equations are still true. How we go there is, as I said, you multiply the two equations, left and right, by the same value, and you sum. So you obviously get this result. Now, of course, why do we do this is because that way the right side of the equation are the same. Therefore, we can equate the left part of those two equations, and of course, we obtain by rearranging, we obtain this. This is pretty clear. Now, we have that equation that we obtained, and this equation, I'm going to rewrite it at the top of this slide. The first thing, let's have a look. If R is not equal to S, and we will suppose that the frequency are not degenerate, so they are not the same. So if R is different from S, then omega R is different from omega S. In that case, if we do that, the only way for this equation on the top to be equal to 0 is for the sum to be equal to 0, since the prefactor is not equal to 0. So basically that already proved half of the equation that I wanted to solve, that if R is different from S, the A's are orthogonal. Okay. Now let's have a look at R equal S. Well, if R equal S, the equation is trivially satisfied, obviously, because omega R squared minus omega S squared is equal to 0. So now we have to demonstrate that the sum itself is not equal to 0. If it's not equal to 0, then we can normalize the A's in such a way that the sum is equal to 1, right? So long as it's not equal to 0, we can normalize them. So we are going to show that now. So this would be this is what we want to show, that the sum is not equal to 0. So the result will be obtained from this. So as I said, in this blue box, this is the main result of this screencast, that the A's are orthogonal, and we can write vectors which are orthonormal, the AR vectors there that are actually written explicitly with the unit vectors EJ, the usual thing. So let's just spend another couple of minutes to show that the sum is not equal to 0 in the case of R equal S. So let's do that. We start from the kinetic energy. All right, we start from the kinetic energy, and we know what are the solutions for the QJ. Remember the solution, the real part of the solution for the QJ were related to the cosine, right? And so now we have a dot, so it becomes a sine, and an omega in front. So we obtain this result where I just substituted the solution from the previous screencast in this equation. So I can rearrange the whole thing, and I obtain something like this. Okay? We just demonstrated that the last term, the last sum, the sum over jk, is equal to 0 if R equal to S. Okay? So the contribution to T will only be non-zero if R and S are the same. Because if R and S are different, then that contribution is 0, right? Because there is a term that's equal to 0. So that means that, in other words, the kinetic energy can be written this way. We can drop all the cases where R equal to S. But of course, we know that the kinetic energy is a positive number. It can only be 0 if all the velocities are 0, right? So if absolutely all the velocities are 0, T has to be positive, right? So if the velocity, unless the velocity are all 0, this kinetic energy has to be positive. And that means that if it's positive, since omega square is positive and sine square is positive, then the sum has to be positive and has to be non-zero. Otherwise, the kinetic energy will be equal to 0. So that's basically what I wanted to say in this screencast. Thank you very much. We are going to move to the next screencast in part 4, which will be talking about normal coordinates. Thank you.